Hey guys, here's your little intro to the last new topic in Trig, which is using Trig identities. And so I'll just give you a few details about it before you jump into the worksheet where you're going to get lots of practice and there are lots of little tricks that you'll learn. So here's the premise. There are hundreds of Trig identities. There are simpler ones and there are really complex ones that we can prove, but we'll start with the basics, like this one, which you've seen before. This is an identity that we can prove just using the unit circle. So this is one that now we've established it, we're going to use it in other proofs. And then there are other identities that are less obvious, but still simple. Here's an example of a pretty simple one that we could prove pretty quickly. That's another example of a trig identity. And then there are some just definitional identities like this, like the fact that tangent is sine over cosine. Why? Because by definition, tangent is y over x. And if we define tangent to be y over x, that is sine over cosine, right? So that's a simple definitional identity, which then would mean this is also true. Cotan is the reciprocal of tangent, so cosine over sine. So let me give you a few examples where you'll use these simple identities. We'll start with an example where you can just use the identities to simplify an expression. Okay, so here's a trig expression, and if we want to just simplify this, then we'll use just basic definitions. Cosecant can be expressed as 1 over sine, and secant can be expressed as 1 over cosine, so we'll just see what that produces. Right, so in that step, all I've done is express cosecant as 1 over sine and secant as 1 over cosine, and let's simplify from there. So we end up with sine squared plus cosine squared which, using that identity I just showed you, this is going to equal 1. So we're able to simplify a pretty complex trig expression just by using some of the basic identities. So I'm going to show you 3 other ones, and they'll grow a little bit in complexity, and then you'll have a bunch of practice examples for on your own. Okay, here's another one where all you're doing is simplifying. Okay, so we start with a product of 2 binomials, and if we just go ahead and multiply through, distribute, here's what we're going to get. Sorry, the pattern is a plus b times a minus b, so the result is just cotan squared minus cosecant squared. That's the shortcut. Okay, and then from there, we can use the definition of cotan as cosine over sine, because it's the reciprocal of tangent. So this is going to be cos squared x over sine squared x. And cosecant, remember, we can express as 1 over sine. So this is minus 1 over sine squared x. We we've got a common denominator, so we can add those two expressions. Cos squared x minus 1 over sine squared x. So here we have to be a little bit creative, and this reminds us of the identity sine squared x plus cos squared x equals 1. So let's take that identity and say, all right, what is cosine squared x minus 1? If I take the 1 and subtract it from cos squared x, I'll end up with negative sine x. So we can use this identity to re-express cos squared x minus 1 as negative sine squared x. And then I've got the sine squared x on the bottom. So this gives me negative 1. Okay. So those first two examples are taking a trig expression and simplifying it using identities. And the next two examples I'll show you, you're trying to prove that an identity is true. Okay, so here's the first one. So there's an equation, sine theta plus cos theta cotan theta equals cosecant theta. This is not an obvious truth, so to prove that this identity is true, that's what we're really doing. We've really got this kind of suspended question mark over there, and so logically what we need to do is not assume that the equation is true to begin with, but prove that it is. So we do that by either taking the left side and re-expressing it so that we achieve the right side, or take the right side and re-express it to achieve the left side, or you could re-express the left side and re-express the right side separately and show that you get the same thing. But what you don't want to do is, say, subtract sine from both sides of this equation. That is logically flawed because it's assuming the equation is already true. We also wouldn't want to do things like cross multiply, because cross multiplying is also assuming that the equation is already true. So here's what we can do then. We can express cotan using cosine over sine. Let's see what that does. So basically, let's take the left side and see if we can re-express it. Okay, so that gives me sine plus cos squared over sine theta. And then we're just going to do simple algebraic manipulations, and in this case, I'm going to find a common denominator and add those two. So to get a denominator of sine theta, I have to multiply by sine theta. So if I put this over sine theta, then that numerator becomes sine squared theta. Now I can add the two expressions together. I get sine squared theta plus cos squared theta over sine theta. And then we notice that the numerator is sine squared plus cosine squared. So that is equal to 1. So we get 1 over sine theta. And there we go. 1 over sine theta, by definition, is cosecant. So that's a pretty basic example where we're doing some basic manipulations. It's really just kind of the most common identity that we use in this particular proof. And it's pretty pure. All we've done is taken one side and re-expressed it so that we get the other side. Okay. So one more example I'll show you is pretty complex. And so there are a few tricks that are listed on the worksheet, things that you can try to do to manipulate and see if it gets you anywhere. But some of these are kind of like puzzles. You just have to try something and see if you can, see what you can do with it. And usually there's more than one way to complete these identity proofs. Okay, here's the fourth one I'll show you. Okay, again, that's not an obvious identity, so and just looking at it, it's not very clear what you might do because you have options. You might take secant and express it as 1 over cosine. You might take tangent and express it as sine over cosine. You might do the same thing on the right side. So it isn't immediately obvious what you would do, and for this one, you might try several things and still get stuck. So here's one trick that you can do. Actually, I'm going to have to rewrite this so it's a little bit more centered. Need a little bit more space on this one. Right, so one of these algebraic tricks that you can do would be to multiply one side by a conjugate. And remember, a conjugate means, like in this case, I've got secant minus tangent. So I can multiply by secant plus tangent over secant plus tangent because that equals 1. Right, so if I multiply that right side by secant plus tan over secant plus tan, this is allowed because it's just multiplying by 1, but look what it produces. So in this case, I'm leaving the left side of the equation alone, and I'm re-expressing the right side. So I get secant plus tan in the numerator, and then on the denominator, I'm going to get secant squared theta minus tan squared theta. Again, because the pattern is a minus b times a plus b. And now, here's an identity that comes in handy. I've got 1 plus tan squared equals secant squared. So secant squared minus tan squared then is equal to 1. So I can spot the identity that is useful in this case. And then I can simplify the numerator to be 1. So this is secant theta plus tan theta. And there we go. That is the left side of the equation, so we've shown that they're equivalent. So there are a whole bunch of examples on this worksheet 3 for solving equations. And so you'll practice a whole bunch of these different tricks. And I'll be clear about which identities you'll need to memorize, like the simpler ones, and which ones you don't need to bother memorizing. They'll either be provided or they'll be easy to recreate on your own. Okay?